native false non-match rate. So the image quality scores for dataset S8 and the minutia count analysis did not really show deviation from any of the other datasets. Consistency of placement also did not reveal any specific issues because S8 actually had really high consistency rate of placement with other interoperable datasets. So then the idea was to create a ridge spacing profile which measured the distance between successive ridge lines. So the process, just again a very general overview, was to skeletonize the fingerprint image, detect the position of the core, and traverse 100 pixels in the y direction and detect the change of color from white to black. So that is essentially detecting a ridge line. Use the IMPROFILE procedure in MATLAB. It's an inbuilt procedure, and you see the output along the y-axis. On the left, you see a fingerprint image from the S8 dataset. On the right, you see a fingerprint image from the S3 dataset. And if you look at the graphs, the spikes indicate where ridge lines were observed in the fingerprint image. And you see that for the S8 image, the ridge lines were observed a lot closer compared to the S3 dataset. So then the S8 dataset was basically transformed so that its ridge spacing profile was more similar to the S3 dataset. And once that was performed, the new dataset was called S8 prime. The false non-match rate dropped dramatically from 100% for its original dataset to 6.43, as you can see in the table with the yellow boxes. So the S8 prime and S3 dataset actually showed quite a reduction, but the S8 prime dataset also showed a reduction in false non-match rates with the S4 and S9 dataset, which was pretty dramatic. And looking upon further analysis, we saw that there was a transitive property, there was transitive nature to this phenomenon. S3 and S4 and S3 and S9 had the lowest interoperable error rates. So when S8 prime was changed so that it would match well with S3, it also matched well with S4 and S9. So some of the conclusions that we had from the study, the minutia count similarity between data sets did not show a relation to a specific acquisition technology or an interaction type. But we did notice that similarity of image quality was more common among fingerprints collected from the optical touch sensors, and this might have to do with the fact that they were all touch type sensors. The similarity of minutia count and image quality did not really have an impact on similarity of false non-match rate, but it did have an impact in reducing the absolute false non-match rates for the interoperable datasets. And one of the datasets that actually stood out was the interoperable datasets of S9 had similar false non-match rates to the native datasets, but S9 did not really show similarity of image quality or minutia count. So that was one of the interesting conclusions. We also noticed that the interaction type and the false non-match rate were more positively related compared to the acquisition technology. This was when the data sets were actually regrouped just by the acquisition and the technology type. And consistent interaction had a positive impact on reducing the false non-match rate, which was, and that impact was also seen on interoperable data sets. We noticed that removing low-quality images did not really make false non-match rates more similar. So one of the avenues of further research is to look more deeply into what's going on, what types of variances are reduced when low-quality images are removed from the data sets. And consistency of ridge spacing seemed to be the most important factor. So that is one of the main future works that has come out of this is to develop a detailed ridge spacing profile, which can be used in a more sensor-agnostic transformation process. Right now, a lot of distortion compensation models have been created, but they heavily rely on sensor characteristics. What kind of sensor was a particular image captured from? We are trying to create a sensor-agnostic way of doing distortion compensation. And like I mentioned before, the performance metric used for this study was false non-match rates. Future work and work going on right now is looking at how does the false match rate, how is the false match rate impacted by these native and interoperable data sets. And we collected a lot of skin characteristics for this study, but we didn't really get a chance to analyze them in depth. So skin characteristics have an impact on image quality. So the idea is to look into how do you control the skin characteristics so that you provide better quality or more consistent quality images. That's the end of this presentation. Tried to give you a very brief overview of the work that was done. And if you have any questions, I think there's five more minutes left.
So maybe I have a question if nobody else. So, and what else can one do to improve interoperability of sensors? I mean, you mentioned one direction in your work, but are there others?
So, looking at this work, and not a whole lot of work has been done in this area. The consistency of placement seemed to be a very important factor in improving interoperable dataset rates. Also, usability issues. So that ties back with consistency of placement. But the rich spacing profile that we are looking at seems to have the most impact on improving interoperability.
But then how can one make sure that the placement is consistent? I mean, how can you do that?
And that is a very important question. Some of the work that's being done is how do you make the user design more intuitive so that when the user actually approaches the device, they know what to do, how to interact with the device, what kind of feedback is the system giving the user so that the user can change their placement if they need to. So until now, a lot of work has been done on improving the metrics side of the biometric system, and we are trying to bring the focus back onto the human, the bio side, so that there's interaction between humans and the systems. We need to look at both those components to actually improve performance of the overall system.
Okay, so
you said you weren't looking at algorithms, but what do you know about those? Would you say that there are probably 9 different algorithms and 9 different devices?
In terms of matching algorithms, yes, I would say that there are at least nine different matching algorithms, but they all the way they actually use the minutia points is what is different. The way they do the detection of the minutia points and the characteristics used to define the minutia points is a standardized format. But then internally they all use these minutia points differently. Some use graphing algorithms, some use Euclidean distance algorithms. So how they use these minutia points is dependent on their application.
Do you know of anyone who's doing what you're doing, but studying the algorithms?
We have one of my other committee members, Dr. Hail Kim from Inha University in Korea. He has a couple of PhD students who are looking at distortion compensation using the algorithmic perspective, so that interoperability can be improved from the system perspective.
Are there questions? No. Okay, thank you.
Thank you.